Am I recording? Yes. Okay. Hopitals rule. This is a method for solving limit problems. It's actually one of the applications of derivatives. So in order to be able to use this method, you need to remember how to take the derivative of different functions. All those rules that we learned in Cal 1, like product rule, quotient rule, the chain rule, we're going to use them in this technique, L'Hopital's rule. And basically, it is used when you're solving a limit problem and you have one of these two indeterminate forms, either 0 over 0 or infinity over infinity. And we're going to look at some examples of both of them in this document here. By the way, this document is already on Leia. I have posted that on Leia, so I encourage you to download it and use it as I discuss the examples. So here's the L'Hopital's rule. Suppose f and g are differentiable functions, and you have a limit problem like this. As x approaches a. And when you do the direct substitution, that is when you plug in a into f and plug in a into g and you calculate, you either get 0 over 0, you get this indeterminate form, or infinity over infinity. Oh, by the way, the reason that we're going back to the limit is that after this section, we're going to look at improper integrals. Improper integrals are, for example, one type of them is when you have infinity as one of the limits, one of the bounds. For example, the lower bound could be minus infinity, the upper bound could be infinity. And then those integrals are solved in terms of limits. So that's why we're going back to the limit problems and we're using this technique, very easy technique to solve these problems. So if you have this limit problem and it's an indeterminate form of the type 0 over 0 or infinity over infinity, then this limit is going to be the same as the limit as x approaches a of the derivative of f, f prime of x, over the derivative of g, g prime of x. And hopefully this new limit is going to be easily done by direct substitution, because if f prime is easier, is a simpler function than f, or if g prime is a simpler function than g, then we are going to a limit problem that's simpler than the one we started with. So sometimes it happens that this new limit is also an indeterminate form of the type 0 over 0 or infinity over infinity. Then we can use the L'Hopital's rule a second time, or a third time, or a fourth time, until we get the answer. And of course, for this equation to hold, these limits must exist. Yes, so provided that this limit here exists. So let's take a look at some examples. So here we have some notes. If the limit on the right does not exist, or if it is infinity or negative infinity, then the limit on the left also does not exist. If the limit on the right, so this one here, still gives an indeterminate form of the type 0 over 0 or infinity over infinity, then we keep using L'Hopital's rule a second time. And there exist other types of indeterminate forms, like 0 times infinity and infinity minus infinity, which we're going to discuss later on. Basically, there are 7 different types of indeterminate forms, and we're going to look at 4 of them in this document: 0 over 0, infinity over infinity, which are done directly by the L'Hopital's rule. We also have 0 times infinity and infinity minus infinity, which we can deal with by doing some algebra and transforming them into either this form or this form and then use L'Hopital's rule. So we'll see examples of that today as well. Okay. Any questions so far? Okay, let's take a look at the first example. We have the limit of 5x to the power of 3 minus 13x squared plus 6x over 4x to the power of 2 minus 13x plus 10. So this is a rational expression, and that's a polynomial over a polynomial. For this type of, it's going to be continuous on its domain. So in order to solve this limit problem, you would do direct substitution first. That is, you're going to plug in 2 for x into the numerator and into the denominator. And if you get a number, then that would be the answer, and that's the end of the story. But in this case, if you plug in 2 into the numerator or into the denominator, you're going to get 0 over 0. That's an indeterminate form. So normally what you would do in Cal 1, before you know anything about the derivatives, is you try to solve this problem by long division or by factoring. That is, if if x equals 2 gives you 0 here, it means that this is going to be divisible by x minus 2. This is also going to be divisible by x minus 2, so you can factor x minus 2 and then cancel it, and that's the way you solved it in Cal 1. But now, with that, we know how to use the derivatives, and we know about L'Hopital's rule. We're going to take the derivative of the numerator, which is going to be 15x squared minus 26x plus 6. Take the derivative of the denominator, which is going to be 8x minus 13. And now if you plug in 2, you get the answer. That's going to be 14 over 3. So that's it. You plug in 2 here in the numerator, you get 14. You plug in 2 here, you're going to get 16 minus 13. That's 3. And that's so easy. We're good? Don't forget that with the L'Hopital's rule, you will not be able to use this equation here unless you have either this form, 0 over 0, or infinity over infinity. So that's why you need to check. And I checked it over here. It's 0 over 0. Then I used L'Hopital's rule. And this checking you need to always do, because if you just jump into the L'Hopital's rule without checking, you may get the wrong answer. Let's do another one. Example 2, limit 10x plus 5 over 3x squared minus 7x plus 4 as x approaches infinity.
Sir, I do have a question.
Yeah, go ahead.
Yeah, for the first one, why don't we multiply 15 by 2?
Multiply 15 by 2 with this 15 here.
Yeah.
We multiply that by, we have to plug in 2 into the equation here. So when you plug in 2 for x, you get 2 squared. That's going to be 4. And then 4 times 15 minus 2 times 26 plus 6. So 4 times 15, that's 60. 60 minus 52. Yes. And then plus, that will give you 14.
Okay, so we applied the derivative only one time.
Yeah, for this one, we didn't need to do it twice, because when we took the derivative, when we used the L'Hopital's rule only once, we got this. And then at this point, when you plug in 2, you get the answer. You don't need to do it again.
Okay.
Actually, you cannot use L'Hopital's rule for this one because it's not an indeterminate form. Yeah, this limit here, it is not an indeterminate form. That's a function which is continuous at 2. When you plug in 2, you get the answer. And that's the answer. 14 over 3 is a number, and that's the limit. Yeah, but before that, in this step, when you plug in 2, you get 0 over 0. So that tells you need to use L'Hopital's rule. Is that clear?
Yes, thank you.
Sure. Now, this limit, when you plug in infinity, you're going to get 10 times infinity plus 5, that's infinity. At the bottom, you get 3 infinity squared minus 7 infinity plus 4, that is also infinity. Geometrically, this is a line with a positive slope, so it goes to infinity. And this one is a parabola that opens up, so it goes to infinity on either side. So this is infinity over infinity. That means I can use L'Hopital's rule. So this is going to be limit as x approaches infinity of the derivative of the numerator is 10. The denominator is 6x minus 7. Okay, at this point, if I plug in infinity, I'm going to get 10 over infinity. In other words, on top, I have a constant number, 10, doesn't change. At the bottom, I have something that approaches infinity. So that's going to be 0, right? Is that clear? If you have a fraction and the numerator is a constant and the denominator is increasing without bounds, then that fraction is going to approach 0.
So, sir, anything like a constant over infinity will always be equal to 0?
Yes.
Okay.
You know, infinity is not a number, yes? It's a symbol. So in this case, this infinity here, this symbol here means that the denominator keeps increasing. So you have a constant over a changing denominator that keeps increasing and going towards, keeps increasing without bounds. So the whole thing, 10 over this expression here, 6x minus 7, is going to approach 0. That gets closer and closer to 0. And then we have the limit of e to x over 1 minus cosine of x. So this example is there to tell you that you shouldn't just jump into the conclusion that this is L'Hopital's rule without direct substitution. Because when I plug in 0 into this, I don't get 0 over 0 or infinity over infinity. What I get is, if I plug in 0 here, I get e to the power of 0 over 1 minus cosine of 0. That's going to be e to the power of 0 is 1, and cosine of 0, that's going to be 0. Sorry, 1. So 1 minus 1 is going to be 0, because cosine of 0 is 1. And now in this particular case, when you have 1 over 0, then it means that the denominator is approaching 0. And depending on whether it approaches 0 from the right or from the left, we are going to have either infinity or minus infinity. So if you have 1 over 0 plus, and by 0 plus, I mean some number that's very close to 0, but not 0, but and positive. So the numbers are to the right of 0, but they're very close to 0. In that case, the whole fraction will approach infinity. But if I have 1 over 0 minus, that is numbers like negative 0.001. This number is very close to 0, but negative. Or here, if I have 0.001, this number is very close to 0, but positive, yes? And this symbol here means the numbers in the denominator are getting closer and closer to 0, but they're positive. And this symbol here means the numbers are getting closer and closer to 0, but they're negative. So this one will approach negative infinity, because positive over negative is negative. So in this case, this is going to be 0 plus. Why 0 plus? Because now cosine of 0 can never be, generally cosine can never be greater than 1. Cosine of x is always between negative 1 and 1. So as x approaches 0, cosine of 0 is going to approach 1 from the left. It's going to approach 1 from the left. So 1 minus a number that's a little less than 1. It's going to be, and it's going to be a positive number. 1 minus a number less than 1. It's going to be 0 plus, so that's going to be infinity. So the reason this example is there is only to remind you that you're not supposed to use L'Hopital's rule right away without checking for the type of indefinite form that you have. Is it 0 over 0? Then use L'Hopital's rule. Is it infinity over infinity? Then use it. But if it's not 0 over 0 or infinity over infinity, then you cannot use it. You have to use another method. Are we good? Okay. Now let's take a look at another example where you can use L'Hopital's rule. Cos x minus 1 e to x minus 1 as x approaches 0. Now in this case, if you plug in 0, you get cos 0, 1, 1 minus 1, 0 on top, and e to the power of 0, 1, 1 minus 1, 0 at the bottom. Okay, so we can use L'Hopital's rule. The derivative of cosine is minus sine x, and the derivative of e to x is simply e to x. Now at this point, if I plug in 0, I'm going to get on top, I'm going to get 0 because sine 0 is 0. At the bottom, I get 1. And what is 0 over 1? That's 0. Okay, next example. I'm going to remind you of a few things. So here, if you want to take the derivative of root x, that's going to be 1 over 2 root x. And then if you want to take the derivative of, let's say, root f of x, then you will have to use the chain rule, and that will become 1 over 2 root f of x, and then you have to multiply that by the derivative of the inner function. So that is the chain rule. Yes, Salma, you have a question?
Yes, can you repeat how you got minus sine x?
That's the derivative of cosine x.
Okay, so we only use the... Okay.
Yeah, because the derivative of the minus 1 is going to be 0. The derivative of cosine x is minus sine x.
Okay, so we only apply the derivative?
Yeah, that's what you do with L'Hopital's rule. You take the derivative of the numerator. In this case, it's going to be minus sine x. And at the bottom, you take the derivative of the denominator. The derivative of e to x is e to x.
Okay.
And the derivative of minus 1 is 0.
Cool, thank you.
Sure. And another thing that I think down the line I'll be using, for example, example 6 here, we have ln. So let me also remind you of that. If you have the derivative of, let's say, ln of f of x, then that's going to be 1 over f of x times the derivative of f of x, which I can also write as f prime of x over f of x. So here I'm using the chain rule again for ln. So these things I'm going to use for examples 5 and 6. Are we good? Okay. So let's take a look at number 5. We have limit of 7 root x minus 1 sine x minus 1 as x approaches 1 from the right. Now in this case, I get 0 on top, 0 times 7, 0. At the bottom, I get sine of 0 if I plug in 1. Sine of 0 is also 0. So that means this problem, this limit problem, qualifies for the L'Hopital's rule. So let's use it. That's going to be limit as x approaches 1 from the right. The derivative of the numerator is going to be 7 times 1 over 2 root x minus 1. And then I have to multiply by the derivative of the inner function, which is going to be 1 in this case. At the bottom, the derivative of sine is cosine. So I get cosine of x minus 1. And then I have to multiply by the derivative of the inner function, which is going to be 1 in this case. Let's simplify this. Limit as x approaches 1 from the right. get 7 over 2 root x minus 1 times cosine of x minus 1. Now, at this point, if I plug in 1 into this, I'm going to get cosine of 1 minus 1. That's cosine of 0. That's going to be 1. And here I get 0 plus, because imagine that you have x minus 1 and x is something greater than 1 but very close to 1. That's the meaning of this. So x could be something like 1.001 or 1.0001. So something very close to 1 but to the right of 1. So what happens to x minus 1 then? That's going to be something very close to 0 but positive. And root something very close to 0 but positive is going to be something very close to 0 but positive. So generally the denominator is going to be 7 over 0 plus, which is going to be positive infinity. Are we good? Okay, example 6. So before I do this, I reminded you of the formula for the derivative of ln of f of x. I'm going to repeat that here. That's going to be f prime of x over f of x. And also, I would like to remind you of how the ln of x looks like. That's y equals ln of x. So ln of x is a function like this. The domain would be all positive numbers, and y will approach infinity as x approaches infinity, and y will approach minus infinity. Y will approach minus infinity as x approaches 0 from the right. So when x approaches infinity, y also approaches infinity. So this function gets bigger and bigger. It increases to infinity, even though it's going to increase to infinity very slowly. But generally, as y approaches, as x approaches infinity, y also approaches infinity. So this is going to keep increasing forever. And what happens as x approaches 0? So here x approaches infinity, and here x approaches 0 plus. So what happens as x approaches 0 from the right? The values of the function are going to get smaller and smaller and smaller, and they're going to go towards negative infinity. So y approaches negative infinity as x approaches 0 from the right. So the limit of ln of x as x approaches infinity is going to be infinity, and the limit of ln of x as x approaches 0 plus is going to be minus infinity. So just wanted to quickly remind you of these limits, and now I think we are ready to do example 6. Any questions? We have limit as x approaches infinity 3 ln of 5x plus 3. At the bottom we have 2 ln of x plus 4. So if I plug in infinity, I'm going to get ln of infinity over ln of infinity. That's going to be infinity over infinity. I can use Hopitals rule. Limit as x approaches infinity. On top, I get 3 times the derivative of the function is going to be 5. That's the f prime of x over the function itself, 5x plus 3. And at the bottom, I get 2 times the derivative of this is just 1 over the function itself. And then I simplify that. I'm going to get limit of 15x plus 4 over let's see, I have 2 5x plus 3. So if I simplify it, I get this as x approaches infinity. So at this point, yes?
Like, it's 3 times 5 over what plus 3?
Oh, yeah, it's 5x plus 3. It's the function. It's the same function that we have over here. Yes, it's actually the derivative of ln of f of x, which is going to be f prime of x over f of x. You're good?
Yeah, thanks.
Okay. Now, this one, if I plug in infinity, I'm again going to get infinity over infinity. So that means I can use the L'Hopital's rule again. Let me just expand the numerator and the denominator completely. I get 15x plus 60. At the bottom, I get 10x plus 6. And at this point, if I use L'Hopital's rule, I have the derivative of this, which is 15, over the derivative of this, which is 10. So that's the answer, 3 over 2. So for this problem, I had to use the L'Hopital's rule twice because I came across infinity over infinity twice.
Sir, what's next to the 6? Like we have 15x plus 6. What is the circle?
10x plus 6.
No, 15. The one over 15x.
Oh, that's just 15 times 4, that's a 60.
Okay.
Yeah, I just expanded that. No, 15 times x, 15x, and 15 times 4.
Okay, because I thought it was an exponent or something like that.
No. Yeah, the 0 went up a little bit, but it's just a 60. Okay. Now, we have seen enough examples of infinity over infinity and 0 over 0. Now let's see what happens with the other indeterminate forms, 0 times infinity or infinity minus infinity. So if you're dealing with the limit of this form, f of x times g of x, as x approaches whatever, then it's possible that one of these two functions approach 0 and the other one approach infinity. And then you'll get 0 times infinity. 0 times infinity. So what do we do in these cases? Do you agree that if I have a times b, I can write that as a, I can write that as a over 1 over b. And then if I simplify this, it's going to be again a times b. Or I can write that as b over 1 times a. 1 over a. And if I simplify that, I get back a times b. And the same thing is true about f of x times g of x. The f of x times g of x can be written as f of x over 1 over g of x. Or it can be written as g of x over 1 over f of x. What is good about this? We have converted a multiplication which can result in this type of indeterminate form into a division. We have created a fraction. So this fraction here might transform this indeterminate form to either 0 over 0 or infinity over infinity, depending on which one of these two I'm using. And in both cases, I'll be able to use L'Hopital's rule. Of course, there will be a smart choice. Sometimes this is the right thing to do. Sometimes the other one is the right thing to do. And how do you know? By trial and error. So for example, it's probably not a good idea to create, if you have ln, you keep the ln on top. So I mean, like this example that we have here, I'm going to explain using the example. If you have limit of x times ln of x, as x approaches 0 plus, yes, I can write this as limit of, I can keep the ln of x on top and move the x down. And then I have to flip the power. This is the same as having 1 over x as x approaches 0 plus. Or I can write it like this. Keep the x on top and move the ln of x down. And algebraically, both of them are correct. Yes. But the one that's going to help us is going to be this one. This is actually b of type infinity minus infinity actually over infinity. That means I can use L'Hopital's rule. This one is going to be of type 0 over 0. That means I can use L'Hopital's rule. But with this one, if I take the derivative of the denominator, it's going to get more complicated. The derivative of ln of x is simply 1 over x. It's less complicated than ln of x. But the derivative of ln of x to the power of -1 is going to be negative ln of x to the power of -2 times the derivative of the inner function, which is 1 over x, using the chain rule. So you see, it gets more complicated. So you will see that this is not the right path. And this is the good one, which will help us solve this problem. So you will see that by trial and error. But generally, out of experience, I know I should keep the ln on top. So let's see how we can do this problem. We have limit x approaches 0 plus x times ln of x. I'm going to write that as ln of x on top, x to -1 at the bottom, x approaches 0 plus. As x approaches 0 plus, ln of x approaches -infinity. And as x approaches 0 plus, 1 over x, because x to -1 is the same as 1 over x. As x approaches 0 plus, 1 over x approaches infinity. So that means I can use L'Hopital's rule. By the way, for the L'Hopital's rule, you can have infinity over infinity, you can have minus infinity over infinity, you can have infinity over minus infinity, you can have minus infinity over minus infinity. All of them are good for L'Hopital's rule. And in this case, I have minus infinity over infinity. So let's use L'Hopital's rule. Limit as x approaches 0 plus, derivative of ln of x is 1 over x. The derivative of x to -1 is negative x to -2. So if I simplify that, this is like having limit of 1 over x over -1 over x squared. As x approaches 0 plus, that's limit as x approaches 0 plus of x squared over minus x. That's like having minus x. If I simplify more, and now this limit is 0, because if I plug in 0 into this, I get the answer. It's going to be 0. Are we good? So if you keep the x on top and move the ln of x down, and you use L'Hopital's rule, your limit is going to get more complicated, and then you know, okay, that's not the right way to go. I have to keep the ln on top. Another example. Limit of x times tangent of 1 over x as x approaches infinity. So again, it's going to be infinity times 0, because if I plug in infinity into this, I get tangent of 0. Tangent of 0 is 0, and 0 times infinity, that's an indeterminate form. Yes, Tiffany?
Yeah, I just had a question for example 7. If it's minus x and we plug in 0 from the right, is it not 0 from the left?
That's 0.
It's just 0, okay.
Yeah, because limit is about approach. Yes. So the question is, what does minus x approach when x approaches 0. It could be 0 from the right or from the left. In this case, from the right. When x approaches 0 from the right, minus x is going to approach 0. So the graph is going to be like this. That's y equals minus x. Now, x approaches 0, so we're here. X approaches 0 from the right. What happens to the y values of this function? They're going to approach 0 from the left. But basically, they're going to approach 0.
Okay, yeah, that makes sense.
Okay. So we have limit of x times tangent of 1 over x as x approaches infinity. So tangent of 0 is 0 and x approaches infinity. So this is going to be of type z, infinity times 0. That means I have to put one of these two functions in the bottom and also give it a power of -1. So again, out of experience, I know it's a better idea to put the tangent on top and move this x down and write it as x to the power of -1. Now this becomes 0 over 0 because tangent of 0 is going to be 0. And if I have x over 1 and x approaches infinity, sorry, 1 over x, if I have, this is the same as having 1 over x. As x approaches infinity, the whole fraction is going to approach 0. So now this is of the type 0 over 0. That means I can use Hopitals rule. The derivative of tangent is secant squared. And then I need to multiply by the derivative of the inner function because of the chain rule. And the derivative of x to -1 is negative x to -2. At the bottom, I have this function, which I take the derivative, is going to be negative x to -2. So fortunately, these two cancel out. This is going to be limit as x approaches infinity of secant squared of 1 over x. Now notice that secant of x is 1 over cosine of x. So secant of 0 is going to be 1 over cosine of 0, and cosine of 0 is 1. So secant of 0 is 1. Now in this case, when x approaches infinity, 1 over x approaches 0. So we have secant of 0, which is 1 squared. That's going to be 1 squared. That's going to be 1. Are we good? Any questions? Next example. Limit of x to the power of 3 times e to the power of negative x squared as x approaches infinity. So here we have infinity times e to the power of negative infinity, which is 0. That's going to be infinity times 0. So what do we do with this? We just keep the x to the power of 3 on top. We move e to the power of negative x squared. We move it down, but we flip the sign to e to the power of x squared as x approaches infinity. Now this is going to be infinity over infinity. I can use Hopitals rule. It's going to be limit 3x squared e to the power of x squared times the derivative of the inner function. I'm using chain rule again. I get 2x. It's going to be limit of, let's simplify that. We get 3x on top. At the bottom, we get e to the power of x squared times 2. This is going to be infinity over infinity again. So I can use the L'Hopital's rule a second time. Derivative of the numerator is going to be 3. Derivative of the denominator is going to be 2 times e to the power of x squared times 2x as x approaches infinity. Okay, at this point I get 3 over infinity, which is 0. Are we good? Okay, and the last type of indeterminate form we're going to deal with is infinity minus infinity. Very simple example of that, limit of x minus x squared as x approaches infinity. If I plug in, I get infinity minus infinity squared. That's infinity minus infinity. That's an indeterminate form. So what do we do for this one? For this one, it has a very simple solution. You just factor out the x. You get x times 1 minus x as x approaches infinity. So at this point, you can see that this is going to be infinity times minus infinity, which is not an indeterminate form anymore. Infinity times minus infinity is going to be minus infinity. Are we good? So this example is not using L'Hopital's rule. It's just an example to show you how infinity minus infinity should be dealt with. In most cases, you have to begin by factoring out so that rather than a subtraction, you have a multiplication. Next example. You have limit of x times e to the power of 1 over x minus x as x approaches infinity. So this is e to the power of 0, that's 1. 1 times infinity minus infinity. So it's infinity minus infinity. However, if I factor out the x, I get e to 1 over x minus 1. X approaches infinity. So now it's infinity times 0. So I began at something that was infinity minus infinity. I factored out the x, and now I am at infinity times 0, and I know what to do with that. I can write that as limit of, I'm going to keep the e to 1 over x minus 1 on top and move the x down and flip the sign of the power. Yes. So now I have 0 over 0. That means I prepared it for the L'Hopital's rule. I began here at infinity minus infinity. I factored out the x. So now I have infinity times 0. And I moved the x down. I converted a multiplication into a division. And now I can use L'Hopital's rule because it's infinity over infinity. Is that clear? So the next step would be to take the derivative of the numerator and to take the derivative of the denominator. Denominator is going to be minus x to minus 2. The derivative of the numerator is going to be e to 1 over x times the derivative of 1 over x, chain rule, negative x to negative 2. And then, fortunately, this simplifies to e to 1 over x. As x approaches infinity, this is going to be 1. Any questions? So we have 2 more examples and then we'll be done with the lecture. So what do you do with this one? Limit as x approaches infinity of x minus root x plus 2. So for these problems in Cal 1, we learned that you have to begin by multiplying the numerator and the denominator by the conjugate to rationalize the numerator or rationalize the denominator. And by conjugate, we mean if you have a minus b, you're going to multiply by a plus b. If you have a plus b, you multiply by a minus b, and then you use the fact that this is a squared minus b squared. So for this problem, we have to begin by multiplying the numerator and the denominator by the conjugate of the numerator in this case. So this becomes limit as x approaches infinity of, on top, we're going to have x squared minus this root squared. So what is root a squared? That's simply a. So we get x plus 2. At the bottom, we have x plus root x plus 2. If I simplify the numerator, I'm going to get x squared minus x minus 2. That would be the numerator. At this point, if I plug in infinity, I'm going to get infinity over infinity. Notice that by multiplying by this fraction, I changed the format of this function from a subtraction from a difference into a quotient, into a fraction. And that caused the transformation of infinity minus infinity to infinity over infinity, for which I can use the Hopitals rule without changing the value, because this fraction here basically is 1. It's something over itself. So I'm not changing the value of this function. But now I'm changing the indeterminate form. So limit as x approaches infinity. Let's take the derivative of the numerator, 2x minus 1. Derivative of the denominator is going to be 1 plus 1 over 2 root x plus 2. At this point, if I plug in infinity, I'm going to get the answer. It's going to be infinity on top. At the bottom, I get 1 over infinity. 1 over infinity is 0, so it's 1 plus 0. So I get infinity over 1 plus 0, that is infinity. Any questions? Let's do this last example. For this one, I'm using this algebra skill. If I have a over b minus c over d, that's going to be ad minus bc on top over bd at the bottom. So just common denominator is going to be bd. That means I have to multiply the numerator and the denominator of this one by d, and the numerator and the denominator of this one by b. So I have a common denominator, and that's going to be AD minus BC on top and BD at the bottom. For this limit problem, I have a fraction minus fraction. I have x over x minus 1 minus 1 over ln of x as x approaches 1. So on top, I get 1 over infinity, 1 over 0 infinity minus, at the bottom, I get ln of 1. ln of 1 is 0. So again, I get 1 over 0. That's also going to be infinity. So it's of infinity minus infinity type. But if I do the operation, then I go from a difference, a subtraction, into a quotient, into just a fraction, some function over another function. So hopefully this indeterminate form will be transformed into either infinity over infinity or 0 over 0. So let's do that. We get limit as x approaches 1. At the bottom, we have x minus 1 times ln of x. On top, I'm going to have x times ln of x minus 1 times this. So it's going to be minus x plus 1. Any questions so far? So now let's see what happens if I plug in 1. If I plug in 1, I get 0 minus 1 plus 1. I get 0 on top. And I get 0 times 0. So notice that ln of 1 is 0. I get 0 over 0. 0 times 0. So now I can use L'Hopital's rule. Limit as x approaches 1. The derivative of this part here needs the product rule. Yes, so I have two functions, f times g. I want to take the derivative of that. It's going to be f prime times g plus f times g prime. That's the product rule. I need to use that. So the derivative of x is 1 times ln of x plus x times the derivative of ln of x. That's 1 over x. So x times 1 over x, that's 1. Minus 1, the derivative of this part. And at the bottom, I have another product. So I have to use the product rule. The derivative of this is 1 times ln of x plus this function, x minus 1, times the derivative of ln of x, which is 1 over x. Let's simplify this. We get limit of ln of x on top. At the bottom, we have ln of x plus x minus 1 over x, which I can also write like this as 1 plus 1 minus 1 over x, because x minus 1 over x is equal 1 minus 1 over x. So I have this, right? Now what happens if I just plug in 1 into this? If I plug in 1 into this, I'm going to get 0 on top, and at the bottom, I get 0 plus 1 minus 1. That means I get 0 over 0 again, right? So that means I have to use the L'Hopital's rule a second time. Since the limit both the numerator and denominator are still 0, we apply L'Hopital's rule again. So let's do that. So since you have it over here, I'm going to erase this. So we have limit of x approaches 1. The derivative of ln of x is 1 over x. The derivative of ln of x is 1 over x plus derivative of 1 is 0. And then derivative of negative 1 over x is going to be plus 1 over x squared. Because notice that the derivative of x2 minus 1 is minus x2 minus 2. And then there is a minus here. Minus times minus is going to be plus. So at this point, if I just plug in 1, I'm going to get 1 on top and 2 at the bottom. And that's the answer. So for this one, I had to use the L'Hopital's rule twice. Any questions? Okay, so this I'm done with the lecture.